Welcome to this session. This session is on thermochemistry and thermodynamics. When it comes to AP problems, the two are not exactly separate. So I would say that thermodynamics far outweighs thermochemistry, but then again, enthalpy is pretty big throughout all of this, so it's just you just got to think of it as one big grand marriage of thermochem and thermodynamic. And it's a good marriage. So my name is Renee McCormick. I'm with the National Math Science Initiative, and if you've been listening to me before, you know this Texas twang is not going away. So we're going to work through what we typically call essays, but please don't think they're essays like you write in English. These are more just short answer, give me a couple of sentences, but definitely it's not as mathematical as if I say that we're working through an AP problem. We'll do a separate recording on that, but I'm glad that you've started with this. If you didn't start with this, you should have, because this is where a lot of the concepts are. So not only is this good for you in terms of learning how to write about the energy involved, because anytime you're writing one of these essays, which means you do not have a calculator in your hand, you are most likely dealing with an awful lot of energy concepts, and you need to learn to talk about the energy of the system in a mature way that's going to earn you points. But more importantly, a lot of these concepts are going to translate into multiple choice points for you as well. And most of the students I work with were happy to say that it's the multiple choice portion of their unit exams that they have the most struggle with, which is not a surprising thing at all because it's kind of our fault. We don't have a lot of multiple choice questions for you to practice with. However, having said that, if you go to the AP Chemistry NIMSY, which is probably where you got this in the first place, wiki page, wikispaces.com, there is a section toward the end of the entire website that has 3 different sets of multiple choice questions. They're not separated out by like just thermo, but there's 3 times 75 worth of them, and the cool thing is they have all the explanations written out. So you can at least get a glimpse into some pretty darn good imitations of what AP multiple choice questions would look like regarding thermo or any other topic that you seek. Alright, so we're going to get started. When you look at one of these questions and you see this double-edged arrow, you're probably thinking, ooh, that could be equilibrium. And indeed it could. And if it is equilibrium, this solid would get your attention because that wouldn't be in the equilibrium expression. Remembering that the equilibrium expression is equal to products over reactants. And we can do it in concentrations or we can do it in pressures. When gases are present, pressures aren't a bad idea, but you can also still do it in molarities. But we wouldn't have any reactants, so that concentration would essentially stay what it is now, basically 1. And so our K would be pretty simple. It would just be the concentration of the boron trichloride or the ammonia times each other. No exponents necessary because the equation's balanced with all 1s. And then the main thing that you look at, though, is we also have 2 moles of gas. Even if this were an equilibrium problem, I'd still look at this to get the change in the number of moles, and 0 moles of gas. So this 2 moles of gas going into 0 moles of gas is huge when it comes to entropy. So that's going to be a really big drop in entropy. So sure enough, if you actually read the problem, first thing they ask me for is to predict the sign of the entropy change. So as the reaction proceeds to the right, from left to right if you wish, and explain your prediction. Well, we just did. So let me put it down formally in words. First of all, when they ask you to predict the sign, do that right up front. Say negative, or write the word negative, or put this negative in parentheses. I'm going to write negative delta S, just to be real clear. And then explain means you better write me a sentence. It would be nice if it started with a capital letter, ended with a period, and made some sense in between. So something to the gist of, and there are many ways to write a correct sentence about this. I'm going to say, because the system becomes more ordered, which means it's less disordered, hence the negative sign on the delta S, becomes more ordered, as evidenced by 2 moles of gas reacting to form 1 mole of solid, which is a much more condensed state. All right, so there's a lot of different ways you can say it. I chose to say the system becomes more ordered. Equally correct, the system becomes less disordered. I just don't like the double negative thing. It messes with my brain. So any way you want to do it, that was worth 2 points. 1 point for getting the correct sign, 1 point for a good explanation. So moving on to the next piece, if the reaction spontaneously proceeds to the right, oh, they just told you, negative delta G. Predict the sign, again with the sign business, of the enthalpy change and explain your prediction. Well, they just gave you a big giant hint with that negative delta G. So if you know a negative delta G and a negative delta S, perhaps you should go to what I lovingly refer to as the granddaddy equation. Delta G equals delta H minus T delta S. Now, that's also known as the Gibbs free energy equation. So I just have stupid names for things because it seems to help students remember the names better, remember what's going on. I love what Alabama does. Alabama says this is the going home to supper equation, which I think is kind of cute too. So if I rearrange and solve for delta H, excuse me, then what would I get? I would get delta G plus T delta S. All right, so that T delta S term is basically allowing us to do this addition. Delta H is measured in kilojoules, delta G is measured in kilojoules, delta S is typically measured in joules per Kelvin, and all of it's in per mole anyway. So I've got to multiply by the Kelvin temperature to get the per Kelvin out of there so that I can add joules to joules or kilojoules to kilojoules. So that in the problems, it's more problematic, and you have to watch your units much more closely. So in the big idea here, what do we know? We know that delta G is minus. We know that delta S is minus according to our prediction. We know that Kelvin temperatures are always positive, and we know that the T delta S term is added to a negative term. So I have a negative term plus another negative term. So what does that force the sign of delta H to be? Well, it's got to be negative. So I'm going to predict that I'm going to have a negative delta H term. All right, so how am I going to write this out? This is my thought process that you just saw, so now let's actually write this out. The sign of the enthalpy change is going to be negative. So negative delta H. As temperature, I'm on the wrong part. Delta H must be negative since the reaction is spontaneous. Therefore, negative delta G is added to a negative T delta S term, which results in a negative delta H value. So look at you doing math without a calculator. Also doing it symbolically, which we call literal equations. You need to get good at this because if you're going to college, you haven't seen the last of that. If you're taking the AP Physics exam ever, half of the free response is all in letters symbolically like this, in variables, not at all in numbers. All right, so we get 2 points for that as well. We get 1 point for saying that the delta H must be negative and 1 point for being able to explain it. Doing just the math, doing just this that you see up here is not enough. It does enhance your explanation. It does help you visually sort out your thoughts, but you still have to write sentences. So if you don't have a calculator in your hand, you need to switch to the part of your brain that's going to do some easy math, lots of pluses and minuses, especially in thermo, but you also need to understand that you're going to have to be writing some sentences to explain your math. So we'll get another practice at that coming up. The direction in which the reaction proceeds spontaneously proceeds, changes as the temperature is increased above a specific temperature explained. So what we know is going on is we're going from a delta G to a positive delta G. That means we had to pass that in between, right? We had to approach zero, pass zero to actually change the direction the reaction proceeds. So basically we went through equilibrium is what we're after here. So, and this all occurs as the temperature is increased. So I think the easiest way to approach this is kind of get an expression that's going to help you understand what's going on. So I'm coming back to Granddaddy. Delta G equals delta H minus T delta S. We said this is negative. but it's going to switch over to positive at some given temperature. We know that this is a negative term. We know we subtract this term, which we also know is negative. We just figured that out right up here. And so this entire side of the equation is negative. How is this ever going to switch? Well, we're subtracting a negative term. Okay, it's not the equation that I wrote up here where I'm adding the positive term and I rearrange and say solve for delta H. This is leaving it delta G equals delta H minus T delta S. Doesn't this make a positive term? So when I get the temperature high enough, this positive term right here, looks like a little smiley face at the moment, that little positive term is going to overcome that negative term, and is what's going to switch us to 0 and then on over. So now I need to just kind of write a sentence about that. So give myself a little more room here. As temperature increases, and yes, you can do it that way. As temperature increases, you don't have to use real words. The magnitude, as opposed to the sign, of the negative T delta S term, which is subtracted, increases it becomes large enough to exceed the magnitude of the negative delta H term. Thus, the sign of delta G becomes positive, indicating non-spontaneous, or something to that effect. The big idea is that you realize that this term right here is a positive term once we subtract the negative, because it's negative. The T delta S term technically is negative, but once you subtract it, then that's becoming a positive term, and it's going to eventually get large enough with big enough T values, which are positive, to overcome that negative delta H, at which point we'd go through 0, where delta G equals, that whole side of the equation equals 0. That's when we're at equilibrium. And then we're going to shift that reaction back the reverse direction once we exceed that, and we get positive delta G values. All right, coming into the home stretch. What is the value of the equilibrium constant at the temperature referred to in Part C? We love this. You're going to see this over and over throughout this recording if you keep listening. So we love this. We're just going to rearrange this and solve for T. But that's not what they're asking me. But let's go ahead and do it just so you can see it, because you're going to get to see it over and over. Basically, they're saying, look at this. If I wanted to solve for this term right here, what would I do first? Well, I would take that negative over to the other side, so that T delta S is going to equal delta H minus delta G. Did I do my math right? Yep, move that over, my sign's flipped. Okay, and then what? T would equal delta H minus delta G over delta S. Okay, so now that's my thought process. You don't need to write this down. It's just trying to help you understand this, what's going on. Essentially, all you really need to know for this question is what's the value of the equilibrium constant at the temperature where that spontaneity shifts. So they're basically trying to figure out, do you know the following? Do you know that at equilibrium, delta G equals 0, E naught equals 0, I should say E equals 0, back to the thermochem that you've already studied, hopefully, and K equals 1. That's what they're trying to figure out if you know that or not. So I'm going to start my real response now. K equals 1. Since at the specific temperature, and you could have used just a big capital T, at which the sign of delta G changes from negative to positive. I like to put parentheses around it. You don't have to. I just don't want them to think it's a dash. I want them to know it's a minus sign. The system is at equilibrium. Therefore, K equals 1 and delta G equals 0. All right, so you don't have to add that delta G equals 0 bit. That you could leave off. But the big idea, again, is simple. Don't try to overthink it. What's the value of the equilibrium constant, the temperature, where we're going to flip the switch from negative to positive? To flip from negative to positive, you have to go through 0. And when you go through 0, then you're going to actually end up with K equals 1. Delta G equals 0. If it was electrochem twist in here, EO cell would also equal 0. Now, the reason that K equals 1 is because these really are knots on here. The problem didn't give us that, but essentially that's what we're dealing with. And that little knot, remember, is 1 atmosphere, and 1 molar. So it doesn't matter whether you're doing pressures or concentrations on your K value. It doesn't matter if you're squaring, cubing, taking to the 4th power terms. 1 cubed is still 1. And 1 times 1 times 1 over 1 times 1 times 1, or whatever it turns out to be, is all still 1. So K equals 1 at equilibrium, if you're staying with standard conditions. All right, let's move on through the 90s. We're going to go on into 1993, and let's look at this problem. Now, at some point in this recording, you're going to go, wait a minute, these problems keep asking the same sorts of things over and over again. At that point, you are learning what to expect. So I've told you before, when we work through these AP problems, first of all, you should be working through them by yourself without me. So pause me now, work this problem. You already got to see one example worked out. Work this problem, then come back and look at each piece and listen to the explanations, realizing there's many different ways to put this on the page. The way I put it on the page is not the only way that would earn you credit. So, having said that, I want you to be looking for patterns. I need to shift you from being a defenseless student into, oh my gosh, this mean old AP problem, what on earth is it going to do to me next? To, hey, I got this. I know what's happening. I'm working a thermo problem because I see delta S and delta G and delta H on this page without even reading questions that just pop off the page to my little brain. So I'm going to look at this chemical system up here and I'm going to say, hey, how many moles of gas is going on each side of this equation? I see 15 going to a mere 8. That means I got a negative delta S happening here. They tell me this is at 25 degrees Celsius, so my temperature is 298. That means I'm at standard conditions, so I'm talking about a delta S naught. That's the first thing they want me to do, is predict the sign of delta S naught for the reaction and justify your prediction. So we're off to the races. We already could have written that first piece. So negative delta S. How come? Since a more ordered state is formed as evidenced by, and that's my lingo. There's many other ways to say it. I just like the as evidenced by. The reaction of 15 moles of gas to form, or produce, if you like that better, 8 moles of gas plus 10 moles of liquid. Because that's definitely more ordered as well. So, more ordered state, more condensed state, there's different ways to say it, but the big idea is, hey, you went from total chaos of 15, count them, 15 moles of gas, into many, many fewer moles of gas, and some liquid as well. What is the sign of delta G for the reaction, and how would the sign and magnitude of delta G be affected by an increase in temperature to 50 degrees Celsius? And explain your answer. Okay. Well, what do we know what's going on here? Did they tell us anything about the delta H value? No, not so much. They just want to know about delta G based on the fact we have this negative delta S. So, interestingly, my numbers did not move down. My little point values over here. Got distracted. Sorry, forgive me. All right, so one more time. What's the sign of delta G? Well, I don't know yet. I need to think about that a little bit. So it's okay to kind of delay that and think this through using delta G equals delta H minus T delta S. And just kind of think about it. We are told somewhere in here that this is a spontaneous reaction, aren't we? Yes, look at that. Spontaneous reaction. So that means I know negative delta G. There was the piece I needed. A negative delta G, we just predicted. We know that temperature is always positive because it's on the Kelvin scale. So I just said that I predicted that delta S was going to be a big giant fat negative. So I'm subtracting a negative term. So the only way that I can have a delta H, oh, never mind. I'm making this way harder. I'm into the next piece. So sorry. We already know it's negative delta G because they told us it's spontaneous. But to answer the next piece of the question, so negative delta G, we know that. How would the sign and magnitude of delta G be affected by an increase in temperature? That's where I'm headed. So this is going to be negative because we know that this delta G is negative. So let me try this again. I'm not doing a good job here. So can I have a do-over, please? So my T delta S term is negative. Easy enough, because we know that our delta S is negative by loads, and we know our T is positive. So I'm going to subtract that negative term, which makes this whole bit over here actually turn out positive. So as temperature increases, this value is going to get greater and greater, and it's going to eventually overcome this delta H value, which is not multiplied by T. And when that occurs, then I'm going to get a positive delta G. So I'm going to now write my answer. So I'm going to get rid of all my thought process, which I got to say was a little muddled to begin with, and say, all right, I have a negative delta G naught. Now, when you take the real exam, you have these green sheets that you pull out of your test booklet. That's where you do all that scribble I just did. On your white pages, where you actually submit your answers to be scored, you want to make things a little bit cleaner. And I realize you're in a tremendous hurry, so you kind of need to practice this idea of scribbling somewhere else other than right where you're going to put your final answers. So it's a negative delta G since we are told the reaction is spontaneous. You get a point for that, just being able to interpret the word spontaneous. So what they want me to address is the sign and magnitude of delta G when the temperature is increasing. That's what I need to really explain. So I am going to write delta G naught equals delta H minus T delta S. And I'm going to tell you that's negative. I already told you that's negative. I know that's positive. So the question is, how is the sign of the delta H going to be changed? So the T delta S term is negative, but subtracted, therefore ultimately added, to the delta H. Now, nowhere in here has anybody told me about delta H yet, but I know that delta H has got to be negative. Otherwise, I could have never gotten a negative delta G. So therefore, delta H must be negative. Therefore, the magnitude of the delta G term becomes less negative. In other words, it approaches 0. Again, there's many different ways to say this. My dyslexia at work. If t continues to increase, delta G will eventually become positive. And you may have done a more elegant job of that than I did. So let's recap. What's the sign of delta G for the reaction? Negative. How come? Because the reaction is spontaneous. Boom, you got a point for that. Then how would the sign and magnitude, so they're asking for two pieces, the sign and the magnitude of delta G be affected by an increase in temperature to 50, and explain your answer. You got to think it through with the granddaddy equation, where delta G equals delta H minus T delta S. So we already said that delta S was negative. We already know that delta G is negative. So how can I subtract a negative term, which means positive? This entire piece right here is adding. How can that be? How do I get from plus to minus? Well, this term has got to be largely negative. That's the only way that's going to work. So the T delta S term is negative, but subtracted, therefore ultimately added to the delta H term. Therefore, the delta H term must be negative to yield, would make a better statement, a negative delta G naught. Therefore, the magnitude of delta G becomes less negative, as meaning it approaches 0, if T continues to increase. So delta G will eventually become positive. And you can leave that last bit off. But the point values were because you, number one, knew that the definition of spontaneous meant that the sign of delta G is negative. Number two, you used delta G equals delta H minus T delta S somewhere in your discussion. And then finally, for the other piece of your explanation, the words. And the words that actually earned you the point was to somehow communicate delta G was becoming less negative, approaches 0, etc. We don't generally say more positive, because that would be a lie, right? Because it was a negative value to begin with, so more positive just muddies the water. So stay away from that term if you're talking about a negative delta G term to begin with. I still do a lot of this with the vision in my head from second grade of the number line, where it was the biggest day of my life, I think. I've always loved numbers, and I walked into second grade, and the number line that had been on top of the blackboard my whole life in first grade has now moved somehow. Somehow the in the middle of the blackboard is 0, and the positive numbers are still to the right of it, but there were these things I'd never seen before, which were negative numbers. I get in the car that evening, and my mother says to me, "How was school?" as my mother always said to me. And I said, "It was a great day. I learned there's twice as many numbers in the world as I thought of, and why hadn't you told me that?" So I've been a geek for a very long time. All right, let's look at the next piece of this. What must the sign of delta H naught for the reaction be? I personally, if I had constructed this question, would have asked that before part B, because we had to stumble upon that. So we already had that thought process, so now we just get to write it down for points. So delta H naught must be negative. Since delta G naught is negative, that's all I really need to say. How? That's what must the sign be? I'm going to do the math one more time. Delta G naught equals delta H minus T delta S. We know that the T term is positive. We said that the S term was negative. We're subtracting this. So equals a negative term. I'm going to just put in delta H naught there. So this becomes positive and added. Must be negative to yield negative delta G value. All right, so That's my thought process. And it's okay to have that scribbled down somewhere and think that through. So how does the total bond energy of the reactants compare to that of the products is the second piece of this equation. Or this question. So since delta H naught is negative, energy left the system. Therefore, you got to think about this. Therefore, the bond energy, I'm going to use BE, the bond energy of the reactants is less than the bond energy released as products. Product, singular. Bonds, plural. Form. All right, so what's the scoop? Well, there's two parts to this. You're going to get a point for each part. First of all, you got to convince them that delta H has to be negative, and that you're going to have to do with the pluses, the minuses, the math, basically, in the granddaddy equation, Gibbs free energy equation. Then you have to reason with the bond order. It takes energy to break bonds. So reactants is bond energy in, or the cost, and products is bond energy out, or the payoff. Well, if you have a negative delta H, that means heat energy exited the system, exothermic, exited, left the system, lost, minus sign, all those connections in your brain. So that means that more energy was released, exited, lost, left the system when the product bonds formed. So when a bond forms, energy is released. It costs you energy to break a bond. So you got a point for the explanation and a point for explaining why delta H had to be negative. Then, finally, when reactants are placed together in a container, no change is observed, even though the reaction is known to be spontaneous. All right, let's think this through. Energy, reaction progress, time if you wish. If I have a negative delta H, that means the energy of the reactants was higher than the energy of the products. Now, you've seen a graph that sort of starts off this way before, many times, many times, and that's the bottom line for thermo. That's it, just these two dashes with all this disconnect in between. But what you often see is this piece that connects the two together. And this amount of energy versus this amount of energy, the change therein is what we call enthalpy. And because we started at high energy and we ended at low energy, some energy was lost, and so we put a minus sign on that. This amount of energy is called the activation energy, and that's what this question is referencing. When the reactants are placed together in a container, nothing's going to happen until you have it warm enough, or you spark it, or whatever it takes to give it that boost of activation energy. That's what spontaneous means. A spontaneous reaction is spontaneous after the activation energy has been achieved. Once you've got it going, then it continues to go. But you've got to give it enough energy to get over that energy hump, so to speak. So if you put these together in a container and you know that this is a spontaneous reaction but nothing is happening right away, then it just means that the reaction has a high activation energy. So the reaction has a high activation energy, which you can abbreviate EA, E sub A. Spontaneous reactions occur without additional energy added beyond the activation energy required to start them. Again, you may be a better writer than me and made that a much more eloquent response. But that part also was worth just 1 point. So you got to be clear on this question that's asked a lot. You haven't seen the last of it. Put those reactions together, no changes observed, even though the reaction is known to be spontaneous. That's a classic question, just a classic question. All right, let's move on through some more of the 90s. At any point when you get this, you feel free to stop listening. I hope you use these recordings in a productive way. I hope you really do work the problem first, because just watching me work it won't help you because, hey, I know this stuff. You're the one who's trying to learn it. But secondly, there's no reason for repetition when you already get it. There's only reason for repetition when you don't. So as you use these recordings, I hope you kind of fast forward and go, okay, I know how to do that part, fast forward to the next part, and the next part, and you figure out what it is that meets your needs. That's the intent of these. All right, 1994. At 298K, the standard enthalpy change delta H. As soon as I start seeing this delta H, this delta S, I'm going to start thinking about the moles of gas and what's going on with the disorder in the system. So I've got 3 moles of gas going to 3 moles of solid. Well, there's a big drop in chaos. Plus 2 moles of gas. So even if everything was a gas, the number of moles matters. But what you're really focusing on first is moles of gas going from gas to liquid to solid. But even if everything was a gas, the side that has more moles of gas would be more chaotic, more disordered than the side that has fewer moles of gas. So as 298, the standard enthalpy change for the reaction is represented above, and it's a negative. Therefore, it's obvious you have a negative delta H value. To me, it's also obvious that I have a negative delta S value based on these moles, the 3 moles of gas making 3 moles of solid plus 2 moles of gas. So predict the sign of the standard entropy change for the reaction and explain the basis for your prediction. So negative delta S, since a more ordered state is formed, as evidenced by 3 moles of gas. It's not a pretty 3. Reacting to form 1 mole, not 1 mole solid, 3 moles solid. And 2 moles gas. Okay, I will take those 2 points and run. I got a point for putting the negative sign on the delta S and a point for explaining it. What do we have next? At 298K, the forward reaction, i.e. toward the right, is spontaneous. What change, if any, would occur in the value of delta G for this reaction as the temperature is increased? Explain your reasoning using thermodynamic principles. All right, so when they say using thermodynamic principles, that's code for just go to Granddaddy. And anytime you start comparing delta G's after you just did a delta S thing, this is where you need to go. Delta G naught equals delta H naught minus T delta S naught. So what did we just say? We just said this was negative. We know that the Kelvin temperature is positive. This entire term is now negative and subtracted. What else do we know? They want us to predict delta G because they told us delta H was negative. In this roundabout way, we knew that if you lost energy with that minus sign on it, then this is a negative term. All right, so as temperature increases, the delta G term becomes less negative. All right, it's because they told me right here it's spontaneous. So I know that this is a negative delta G naught term. So it becomes less negative as it's approaching 0. Then 0 at equilibrium. Then positive. What change, if any, would occur in the value of delta G for this reaction as the temperature is increased? Okay, so I need to do the math and think it through with the signs and then translate that over into words. So that piece was worth 2 points, and 1 point was for using delta G equals delta H minus T delta S to explain. The other point was for explaining it correctly and agreeing with yourself on the math, meaning this entire thing right here is going to become a positive term. So as this increases, delta G becomes positive. That's your thought process. You don't have to write all of that. You do need to get at least this far in your writing, but this is the thought process you have to go through. All right, what change, if any, would occur in the value of the equilibrium constant, KEQ, for the situation described, and explain your reason? Well, the forward reaction is exothermic, because they told us it gave off that negative 145 kilojoules. So if I increase the temperature, that's going to shift the reaction back to the left. So I want you to start thinking this way. If they tell you that energy exited the system, it exits as a product. So you can use Le Chatelier's principle on this since they're asking you about the value of the equilibrium constant. So if I added heat into the system, it'll behave the exact same way as adding water into the system or adding, well, just water, because that's a solid, doesn't participate in the equilibrium expression. So stick with just the idea of this water vapor. So if I add this heat in, it's going to shift that direction. So what change, if any, would occur in the value of the equilibrium constant? If it shifts to the left, and the equilibrium constant is generally the ratio of products to reactants, and I'm shifting away from product, that means my numerator is going to get smaller. And if my numerator gets smaller, while my denominator is going to get larger as well, doesn't that make my overall value smaller? Just got to think, are you smarter than a 5th grader, Jeff Foxworthy? Fractions. So what change, if any, would occur? KEQ would decrease. Since the forward reaction is endothermic, oops, wrong word, exothermic. Therefore, increasing temperature will favor the reverse reaction. And the value of KEQ would decrease. I'm repeating myself. Now, you could have used the math side of delta G equals minus RT ln K. You could have easily gone through that math and written that explanation as well. So if you did that and you did it properly, then you still get these 2 points. I just think it's easier and faster to think about Le Chatelier since they gave us this question about equilibrium. They gave us all the information we needed to do that. My brain's going to go there first before I have to go to anything more complex. So finally, the absolute temperature at which the forward reaction becomes non-spontaneous. Okay, so we're switching from spontaneous to non-spontaneous, which means we are traveling through delta G equals 0, which is equilibrium. And I also chant to you over and over, let the question lead you. They just sent you to your equilibrium portion of your brain. So now we're going to get to use it here to determine the exact temperature, at least how we would, to explain how we would. So one more time, the absolute temperature at which the forward reaction becomes non-spontaneous can be predicted. Write the equation that is used to make the prediction. Why does the equation predict only an approximate value for temperature? Well, that's the easier question, because entropy for certain is tied directly to temperature, but you may not realize that so are delta H and delta G. So when we put those knots in there, we're tied to 298. So if we start changing the temperature, then basically we're just only going to get an approximation of what temperature this would occur, because our delta H's and delta S values, as long as and our delta G's, they all start changing a little bit. And so you don't have tables at ad infinitum at every temperature. You only have tables that give you this information at standard conditions. So let's actually put an explanation together here. And when in doubt, start here. All right, so delta G equals delta H minus T delta S, and delta G naught equals 0 at equilibrium. Therefore, if this number goes to 0, can't I say T delta S naught equals delta H? I can. Therefore, T would equal delta H divided by delta S. Now, there's a point for that, so there's the equation that I would use. So I answered that part. And now, why does this predict only an approximate value? Well, the prediction is not exact. Since both of those delta terms vary with temperature. All right, so you got the point for this if you said either delta H or delta S varied with temperature. And I suspect you would have said delta S, because delta S has that temperature term in its units in the denominator, so you know it's tied to Kelvin temperature anyway. But both of these really are. So if you said either or, those values vary with temperature, you still get that point. All right, moving on into a little bit later 90s, let's look at the next one, which is 1997. You can see that these essays are asked a lot. So that's why we're doing this, because you got to get good at them. You got to get good at putting this stuff down on the page. All right, for gaseous equilibrium, so we're going to tie equilibrium in here yet again, it's observed that greater amounts of PCl3 and Cl2 are produced as the temperature is increased. So if I add heat here, then we're going to shift the equilibrium in that direction. So that arrow gets bigger. All right, so that means this is endo. It also means we have a positive delta H value. So that's what all of that was code for. So what is the sign of delta S for the reaction? And explain. See, I would have led with delta H if I'd written this question, but nope. We led with delta S because it's an easier question. So what is it? I've got 1 mole of gas in equilibrium with 2 moles of gas. So that means that I am making a more disordered system, and so that's a gain in entropy. So positive delta S naught, since 1 mole of gas reacts to produce 2 moles. That doesn't look like moles, does it? Of gas products, which is a more disordered state. All right, what change, if any, will occur in delta G for the reaction as the temperature is increased? And explain your reasoning in terms of thermodynamic principles. Granddaddy, granddaddy, granddaddy is what that really means. Keep losing my little twos there. All right, so what's the story? This is one of those moments where if you get it and you go, not again, I get it. Just fast forward. So what's the story on this one? We just said this was positive delta S. Let the problem lead you. We know that this term is positive. So we know that whole bloody term is positive, and it's subtracted from a positive delta H. That was more subtle. That's because they gave us this little hint up here that greater amounts of PCl3 and Cl2, which are products, are produced as the temperature is increased. So as I add heat into the system, that means it's an endothermic process. That means it's a positive delta H. That's how I got that positive. So what they're asking me, what's going to happen to delta G? Well, if I have a positive term and I subtract a positive term, as the temperature is increased, this term becomes, this T delta S term becomes larger, so the magnitude of delta G will decrease. And that's all they're really asking. All right, so delta G naught's magnitude will decrease. And by the way, if delta H is large and I'm subtracting a smaller positive term, then my delta G could be positive to start off. But as soon as that T delta S term becomes larger in magnitude than the delta H term, then we're going to switch sign as well. So we may go through equilibrium. So delta G's magnitude will decrease as the temperature increases, since the T delta S term is positive and increases with increasing temperature. It is subtracted from a positive delta H term. So it is possible that the delta G value will change sign. They haven't given me a clue as to whether my delta G is positive or negative at this point. You don't even need that last statement. I'm just pointing it out to you. All right, if helium, well, good grief. Is helium in here? No. They're trying to trick me. If helium gas is added to the original reaction mixture at constant volume and temperature, what will happen to the partial pressure of Cl2? The answer is not a dang thing. This is a classic, easy question, which my students would have called a trick question. Now, if they'd have asked what happens to the total pressure, that's a different ballgame, because helium's in there and it's banging up against the sides of the container. So carefully worded, well-worded question talks about the partial pressure of just Cl2. For the partial pressure of Cl2 to change, you're going to have to shift the equilibrium. And we knew it was an equilibrium. That was not a trick at the beginning. They gave me these double-edged arrows. So in order for that to happen, we would have to change temperature, and it says at constant volume and temperature, so that's not our culprit here. So I got nothing for them. There's no effect. There will be no effect, since helium is not a factor in the equilibrium expression. Which you may call law of mass action. Some texts and some teachers do that. It's the same thing. More examples of grown-ups that can't get along and agree on one term for something. Therefore, changing I don't want to say changing, let's say adding helium. Adding helium has no effect on the partial pressure of Cl2, thus no effect on the equilibrium. And again, you may have written that more eloquently than I did. So finally, if the volume of the original reaction is decreased at constant temperature to half the original volume, what will happen to the number of moles of Cl2 in the reaction vessel? This is actually an equilibrium question at this point. So again, I have 2 moles of gas versus 1 mole of gas. If you decrease the volume, the equilibrium will shift to favor the fewer moles of gas. I want you to think about a syringe. Your syringe has the plunger set at some quantity. In other words, it's not void of gas inside the syringe. So now you're going to decrease the volume. So you're going to take the syringe and put the plunger down, which is going to increase the pressure of a sealed syringe, right? So you're literally squishing these molecules together to reestablish the original pressure, and the only way you can do that is to have fewer molecules, so you must shift that direction to have fewer molecules banging against the side of the container. So let's try to put that into some elegant words here, or as elegant as I'm capable of. So the number of moles of CO2 will decrease. Since the system will shift, and you could easily have written the equilibrium, whichever way you stated it, will shift left to favor the side of the equation with fewer moles of gas. And there you have it. Each one of these pieces was worth 2 points, 1 point for the answer, and 1 point for the explain, 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 explain. All right, so we're going to finish off the 90s with the question from 1999. That was the year I was first asked to come on to test development committee, but I didn't write this question in any form or fashion because we worked 2 years in advance. But it was a very good year for me. All right, so answer the following questions in terms of thermodynamic principles and concepts of kinetic molecular theory. Consider the reaction represented below, which is spontaneous at 298. What did they just tell you? Negative delta G. Smiley face. I know something already, and I haven't even really read what's going on. I have 3 moles of gas. I have, only solids and liquids. 0 moles of gas. Much more ordered state, so I also know I have a negative delta S. So I've considered these things, and I know 2 things already. That deserves another smiley face, don't you think? So for the reaction, indicate whether the standard entropy change is positive or negative or 0. Justify your answer. You've got to be getting the hang of this by now. Negative delta S, since 3 moles of gas react to form a more ordered state, as evidenced by 1 mole of solid and 1 mole of liquid. Aren't just one of each? Yeah, 1 mole of liquid formed. I should have written products formed. I like that better. All right, that was worth 2 points. 1 for the negative sign, 1 for the elegant explanation. My computer's going a little wacky right there. I don't know why that fixes it. I've just learned that it does. All right, so now what? Which factor, the change in enthalpy, which we know to be, I had changed a lot of things around, didn't it? What the heck happened to my computer here? Something shifted. Negative delta H. So this is negative. Or the change in entropy, which we just said was negative, provides the principal driving force for the reaction. Okay, here's the thing. You're old enough to know that disorder abounds. So making a more ordered state is not natural. So that is not the driving force. So if the entropy can't be the driving force, then the enthalpy has to be. So it's just that simple. Exothermic and more disorder are the 2 favored conditions. We're fighting against the disorder with this one by making a more ordered state. So it's got to be the enthalpy that is driving the show. And I'll show it to you mathematically as well. But common sense-wise, the enthalpy, which is delta H, is providing the driving force. Driving forces are about energy. The driving force, since the entropy is negative. All right, so 1 point for identifying that, and then a point for how you're going to explain it. And there are many correct ways to do this, but I'm going to do it this way. again, what did we say? We said that the delta S was negative. We know that the temperature's got to be positive. We know that the delta H is negative, because we figured that out earlier. And so what's going on here? This term is now a negative term and subtracted from another negative term, which means this term is essentially added. So at some point, we're going to overcome the enthalpy. At that point, it won't be spontaneous, but we know this is a spontaneous reaction. All right, so for delta G to be negative, the enthalpy term must be the driving force. All right, because it's mathematically the only way that delta G can work. So either way, whether you explained it this way with the math or whether you explained it in words the way I did above, you get 1 point for saying that the enthalpy is the driving force and 1 point for your explanation, with or without the math. It showed you both ways. All right, then part 3, my numbering is just, this whole file is just a little messed up. So this is I. This was double I, because this was I. So that one's right. Don't know what's going on here. And this is going to be B. But let's finish off triple I first. For the reaction, how is the value of the standard free energy change? Go ahead, you could guess the rest of this, right? Affected by an increase in temperature, and explain. We'll go back to the math. As this positive term right here keeps increasing, the magnitude of the negative term in the bracket keeps increasing, which is subsequently subtracted, so that's going to make it a bigger positive value added onto a negative value. Ultimately, we're going to shift from a negative delta G through 0 at equilibrium to a positive delta G. So we just got to put that in words. The delta G naught value will become less negative as it approaches 0 and is on its journey to positive, as temperature increases, since the T delta S term is negative, but subtracted, thus added to, and you don't have to write all this, I'm just trying to get it across. The negative delta H term. Now, I will caution you on this one. This one, you cannot use Le Chatelier. And the reason you cannot use Le Chatelier is they're not asking you about equilibrium. They're not asking about the amount of products, the amount of reactants, the value of the equilibrium constant. They're asking about delta G. So Le Chatelier's argument is not appropriate here. I often say Le Chatelier is the most used and abused argument on the free response section of the AP exam, and you really need to use it sparingly, with caution. You need to know when to use it, and more importantly, when not to use it. All right, so part B. Some reactions that are predicted by their sign of delta G to be spontaneous at room temperature do not proceed at a measurable rate at room temperature. We are back to this graph that we already discussed earlier in this file, where we have reactant value, product value. This is an exothermic reaction. This would be an endothermic reaction. The area in between has to do with kinetics and activation energy. So if you're not getting your reaction to proceed, it's because it's got a big old hump for that activation energy when we connect those together. So this question is all about the activation energy. Such reactions have high activation energy values, thus low, or small if you like that better, reaction rates. Low, slow, pick your word, but that's the big idea. Then, a suitable catalyst. Ooh, going to add a catalyst in here. Yeah, that still doesn't affect this or this, so you're not affecting anything about the delta G or the delta H. But a suitable catalyst increases the rate of such a reaction. What effect does this catalyst have on the value of delta G for the reaction? And explain. Not a dang thing. We'll be polite and write no effect. No effect on the value of delta G naught. I want a period, not a comma. The catalyst lowers the activation energy, increasing the rate of the reaction, but has no effect on the value of the free energy. Delta G naught. Okay. I hope you didn't listen to every single word. I hope you use this appropriately and have practiced what you need to practice to be able to do better, because I'm sure there's a quiz in your future. So thanks so much. Have a great rest of your day. Hope to see you next time. There's going to be another essay or two. I don't know how long these files are and how many of them I'm going to have to make, but we got lots of essays to cover. As you can see, we ended with the 90s, but there's a lot through the 2000s. And then we have, loads and loads of problems to work too. So stay tuned.